Okay, this is just a very quick refresher on why we would use Mohr's circle instead of the formulas. You'll get the same answers as you do with the formulas, but Mohr's circle I think is a little bit more enlightening. So the issue that we have with any component is we might have a very sophisticated three-dimensional component that has various loadings, different directions three-dimensionally, might have applied moments and torques going different ways. And what we want to do is we want to know for every point on this body, what is the stress state? Are we close to failure? What is the situation? And so stress transformations is a way that we figure that out based on the loadings that we do have. So the first step in doing that is we assign reference axes. This is something that we come to the problem and we apply our choice of reference axes. So let's say this is X, Y, and Z. The reason we do that is if we can align some of these loadings with our reference axes, then we can calculate things like the normal stress in the X direction, normal stress in Y, tau XY, and so on. And if we can calculate these combinations of stress, then if we know what angle we are with respect to these reference axes, the X, Y, or the Z, then we can find the stresses in those directions. And that's really all Mohr's circle is. And so if we extract a little piece out of our component, let's say we just have a little component that came out of the body there, and we can figure out what is the normal stress in that direction, we'll call that X. What is the normal stress in that direction, call that Y. What is the shear stress? If we've got any combination of three values like that, then we can find out for any angular rotation from the X, Y, or Z axis, we can find the stress components as long as we have plane stress. And so you have to have plane stress to use Mohr's circle. And the way Mohr's circle works, if we blow up our stress component, let's say we have a tensile sigma x, we have a counterclockwise tau xy, we have a sigma y there, and we have a clockwise tau xy to keep everything in static equilibrium. We calculate Mohr's circle, center and radius, and let's say that for this particular problem, Mohr's circle looks something like this. Well, what this tells us now is that any possible combination of normal stresses and shear stresses have to lay on that circle somewhere. So one of the first things that we notice is that there is certainly a maximum normal stress, and you know that as the principal stress 1. There's also a principal stress 2. There's a maximum shear stress, both going in the clockwise and counterclockwise directions. So in order to figure out where or what direction that principal stress is in, we need to know what we're going to reference to. So let's say that we pick the X direction. So if I want to find that plane, the plane in the X direction on Mohr's circle, I just basically need to find the coordinates of sigma x, tau xy. So this point on Mohr's circle represents the X direction. You could do the exact same thing for the Y. Tau xy is going a different direction than it did before because we're on the Y plane now, and so as it turns out, this point up here, if we plot the coordinates sigma y, tau xy, we'll find out that that point is right up here. Interestingly, those two are going to be separated by 180 degrees, but we remember that the Mohr's angle is always twice of the real angle. And so what that means is if we were just going on Mohr's circle alone, the angle between the Y direction and the Z direction would be 180 degrees divided by 2, so 90 degrees. In this case, we could say that to get from the Y direction to the X direction, we have to go clockwise 90 degrees. Well, let's go to Mohr's, so that means we should go clockwise 180 degrees. And that's what you see. So the next question is, we know where the x direction is, it's over here. We know where the y direction is, up here. What is the principal direction? What is the principal angle? And so doing that simply is finding what is the value of this angle. We know that that's going to be twice the real angle, so we know that whatever that angle is, if we start at the x direction over here, we go counterclockwise by theta degrees, which is half the Mohr's angle, we will be at the direction of maximum normal stress or principal stress. And so what that means, we said over here we're going counterclockwise theta, so going counterclockwise, there is some angle. If we redraw our lines on the component at a counterclockwise angle of theta, the stress state in that direction is going to be pure normal stress, principal 1, and then 90 degrees to that, because if we go 180 degrees counterclockwise, 90 degrees counterclockwise here, we find the second principal stress. So that is how to use Mohr's circle. From that we can also find what is the angle between the y direction or the z direction and the maximum shear stress. It all works the same.